In this video, we are starting section 4.6 on the change of basis. So back in section 4.4, we talked about coordinate vectors. So we talked about, when we were given some vector x and we had some basis b, how we can go from that starting vector x and express its coordinate vector. And my notation for that coordinate vector was we put brackets around x and then subscript b. So we talked about, how you can go back and forth between having the original vector x, getting the coordinate vector, or vice versa. If I was given the coordinate vector, how I can recover the original vector x. But now, in this section 4.6, we are going to be working with two bases. So we'll have a basis b and a basis c. So there's two bases. And we are going to be interested in going from one coordinate vector to another. So if I have the coordinate vector of x in terms of the basis c, how can I get from that to the coordinate vector of x in terms of some other basis, or vice versa? How can I go back and forth between these two things? So we're going to express this. We're going to find some matrix that will do this for us, called the change of basis matrix. We'll talk about how we can find that, and we'll show how we can apply it to actually switch between coordinate vectors. And then we'll talk about a couple of other ways we can find this change of basis matrix. Okay, so in this video, I want to talk about what the change of basis matrix is, and I want to motivate this with an example. So let's let V be R2. And I'm going to let B be the set of two vectors, C be this other set of two vectors. It turns out both of these are bases for R2. Okay, and I'm going to let X be the vector 3, 2. So first, let's find the coordinate vector of X in terms of each of these bases. So this is a bit of section 4.4 review. So remember that if I'm trying to find the coordinate vector X in terms of the basis B, what I'm doing is I'm going to try to find the weights that let me write 3, 2 as a linear combination of these basis vectors. So I'm trying to write it as a linear combination of those basis vectors. So to do that, so if I'm trying to find this coordinate vector, meaning if I'm trying to find these weights that make this thing work, I've been solving equations like this going back to chapter 1. We set up an augmented matrix to do this. Okay, so I take the vectors 1, 1, 2, 1, put them on the left, and I augment it with the vector 3, 2, and then I'll row reduce it. I'm going to trust that we can row reduce this, so I'm just going to tell you what this thing row reduces to. So this row reduces to 1, 0 augmented with 1, and then 0, 1 augmented with 1. Okay, and the equations that we get from these now are, I'm going to let the variables be C1 and C2. So C1 is equal to 1 from the top, and then from the bottom row, I get C2 is equal to 1. Okay, so what that means is my coordinate vector, x in terms of this basis B, is a vector whose entries are these weights, the weights of this linear combination. So because the first weight was 1, the first entry of this vector is 1. And then because the second weight was 1, the second entry of the vector is 1. Okay, so I'm going to fill in those values here. So those weights both happen to be 1. So this was the first one, here was the second one. So visually, let's recall, well, what did this mean? Like, what is this representing here? So if I draw some axes, and I'll put some tick marks. So 1, 2, 3 on the x, and then 1, 2, 3 on the y. And now if I draw these two basis vectors, so this first vector 1, 1, so I go 1 in the x, 1 in the y direction. So something like this. That's the first basis vector b1. And the second basis vector was 2, 1. That is going this way. So I'll call that b2. And now if I draw this vector x, so the vector x is 3, 2. So 3, 2 would be somewhere here. So what we're doing when we find this coordinate vector is we're trying to write this vector x as a linear combination of these basis vectors and figuring out, well, what weights would we need to take to get this to work? So, what we've shown from solving this is the weights need to be 1. So that just means if I add those two basis vectors together, it should equal x. And I could check this. If I made a parallelogram using b1 and b2 to add them together, if I made a parallelogram, that vector x lies perfectly along the diagonal of that, which means x is just b1 plus b2. Okay, all right, so the problem said let's also get the coordinate vector of x in terms of the basis c. So x in terms of the basis c, let's do that as well. For this one, let me have you pause the video for a minute to have you try this. Pause it in 4, 3, 2, 1, pause it and try it. Okay, so hopefully you did that. Hopefully you paused it to try it. Let us talk about it. So I'm going to do the same type of thing. I'm going to form an augmented matrix. Now in terms of these basis vectors on the left. So -1, -6, -1, -2. I'm augmenting it with the vector 3, 2 with my vector x. Turns out that if I row reduce this, I'll end up getting 1, 0 augmented with 1, and then 0, 1 augmented with -4. So from this, I'm getting C1 equals 1, and then, oops, let me just space that out differently. C1 equals 1, and then C2 equals -4. So those are the weights that will become the entries of my coordinate vector. So the coordinate vector of x in terms of the basis c, the first entry is 1, the second entry is -4. Okay, so let me just highlight the corresponding things. Here's a 1, and that's the 1. Second value is the -4, and that goes there. Okay, so that was just some section 4.4 practice. How do I find coordinate vectors? And what do coordinate vectors represent in terms of this picture? So the big question that I want to try to answer now is there a way I can switch directly from one coordinate vector to another? Like I can go directly from this coordinate vector to that one. Okay, so the first way, it turns out yes. So the first way we can do it is the following. So notice that above, we wrote the vector x as a linear combination of the basis vectors in B. It ended up just being 1 times the first basis vector, and then plus 1 times the second basis vector. Okay, so this vector here is x, and it equaled 1 times b1 plus 1 times b2. Okay, and I've gone ahead and written that here as well. X equals 1 times b1 plus 1 times b2. And when I have an equation written like this in vector form, I can rewrite it in matrix form. So this right-hand side, I can rewrite it as a matrix where I put these vectors b1 and b2 as the columns, and it gets multiplied by a vector whose entries are the weights of this linear combination. So those weights were 1 and this other one. So those are going to be the entries of this vector. So it's going to multiply this vector 1, 1. So writing it in this equation in the vector form is the same thing as expressing it in this matrix form. And this matrix that has these basis vectors as the columns, back in section 4.4, we call this PB. PB. So we saw this back in section 4.4. All right. And so using that notation, what we have here is that x equals this matrix PB times this vector 1, 1. Well, that was the coordinate vector. That's the coordinate vector of x in terms of the basis B. Okay. So, all right. So we have this equation. All right. So I could do the same type of thing expressing x in terms of the c coordinate vector. I could set up this matrix that has the basis vectors of c as the columns, multiply it by the coordinate vector of x in terms of the basis c, which we got was 1, -4. So I could do the same type of thing with that. And now using this notation for this matrix, I can write this as, the left-hand side is x. This matrix, we call that P subscript c for the basis. And then this vector that's multiplying it is the coordinate vector of x in terms of that basis c. All right, so we have this equation, and then we have this equation in terms of which basis we're working with. So now in both of these equations, we have x equals something. So if I set those equal now, what I get is the following. I get this. So if I isolate the coordinate vector of x in terms of c, which I can do by multiplying both sides on the left I'll multiply by the left by PC inverse. And if I do that on that side, I got to do it over here, multiply by PC inverse. And I know that this matrix PC has an inverse because its columns are a basis. And if I put the basis vectors into a matrix, there's going to be a pivot in every column and every row because it's a basis. So it's going to be invertible. Okay, so if I multiply both sides by PC inverse on the left-hand side, well, this inverse times PC is just equal to I. And I times this coordinate vector just gives me that coordinate vector. So we get the coordinate vector of x in terms of c equals PC inverse times PB times the coordinate vector of x in terms of the basis b. So the question we were trying to ask is there a way we can quickly switch from one coordinate vector to another? And it turns out that this matrix does that for us. I'm going to highlight it. So this matrix is called the change of coordinates matrix. So this is called the change of coordinates matrix from the basis B to the basis C. Because what that matrix does is, I multiply it by a coordinate vector in terms of the basis B, and I output a coordinate vector in terms of the basis C. So it's converting the B coordinate vector to the C coordinate vector. And that's where this name comes from. So, I can also make sense of this formula more visually. So if I draw a picture, I'm going to have this vector here, this oval here represent my vector space V. And my vector x that I'm starting with is in that vector space V. And, we've expressed x in terms of two coordinate vectors. So the first coordinate vector was in terms of this basis B. And when I write that coordinate vector, now this is just a column vector. So it's something in Rn, assuming, there's n entries in that coordinate vector. But, I can also do this. I can also convert that x to a coordinate vector in terms of a different basis, in terms of that basis C. And when I do that, again, I get a column vector. So it's going to be some vector in Rn. Okay, so this oval here represents expressing x in terms of the B coordinates. This oval over here expresses x in terms of C coordinates. So the question we are kind of trying to answer is there some way to get straight from these B coordinates to these C coordinates? Like, is there some matrix A that will do this for us? Okay, and it turns out, yeah. Because, thinking back to this equation that we had here, what this matrix PB does is it inputs this B coordinate vector and it outputs x. So what that means is, if I'm trying to get from the B coordinate vector to x, the matrix that does that for me is PB. So multiplying this coordinate vector by PB will output the vector x. Okay, so similarly, based on this equation, if I have the C coordinate vector and I multiply that C coordinate vector, by this matrix P subscript C, it'll get me to x. So, I have a matrix that gets me from here to here. I'd love a matrix that gets me from here to here, because then I put them together to get this matrix A. So to get the matrix that gets me from here to here, what I'm going to do is, I notice that PC goes this way. So if I'm trying to go the opposite way, then what I need is PC inverse. I need PC inverse. Okay, so overall, I'm going to do this kind of in 2 stages. First, starting with this B coordinate vector, I apply PB to it, and then I'm going to apply PC inverse. So in other words, I'm doing a composition of functions. So I'm applying PB first, and then once I apply that, afterwards, then I'm going to apply PC inverse to do the second half of this. Okay, so, doing this composition of functions, that's the same thing as just writing this as the 2 matrices multiplied, PC inverse times PB. And when I multiply those 2 matrices, that gets me from XB to XC. In other words, that is this matrix that I'm looking for. So that is this mystery matrix A, which we are calling the change of coordinates matrix. So this is another way to kind of visually see why we'd expect the change of coordinates matrix to have this formula. We first showed why that is kind of more algebraically up here, and now we showed why that is more visually down here. Okay, all right. So this is one formula for the change of coordinates matrix. There are 2 others that I want to talk about. So I'm going to flip the page here. In this video, I'm going to talk about one other formula for that change of coordinates matrix. And then in the next video, we'll talk about a 3rd formula. Okay, so what's another way I can get that change of coordinates matrix? So if I start off with my vector x, I can express x as a linear combination of the basis vectors as x1b1 plus x2b2 up until xnbn. So from that, I can write its coordinate vector. So the coordinate vector is a vector whose entries are the weights of this linear combination, which are x1, x2, ... up until xn. Now what I'm going to do is I'm going to take the coordinate vector of both sides of this equation. So you'll notice I've taken the c coordinate vector on both sides of that equation. And that's a valid thing I can do. I'm doing the same thing to both sides. So now the left-hand side, I have the c coordinate vector of x. On the right-hand side, I'm going to use the linearity of this c coordinate transformation to split it up as x1b1, that coordinate vector, plus ... plus xnbn, that coordinate vector. Okay, I'm going to apply linearity one more time to pull these weights out in front. Okay, so x1 is multiplying that coordinate vector of b1 plus ... plus pull the xn out in front. That's multiplying the coordinate vector of bn. So both of these steps right here were because we applied a linear transformation. Taking the c coordinate vector of both sides, that is a linear transformation. We saw that back in section 4.4. So that's why I can do that. And now with this right-hand side, when I have a linear combination of a bunch of vectors, I can express that. I can express that as a matrix where the columns of the matrix are these vectors. So the columns are going to be b1's coordinate vector, ... up until bn's coordinate vector. So that's going to be my matrix. And that gets multiplied by a vector whose entries are the weights. So those are x1, ... up until xn. Okay, on my left-hand side, let's not forget that I have the c coordinate vector. So the c coordinate vector of x. So what I have here is this vector x1 up until xn. That right there, that is the coordinate vector of x in terms of the basis b. That's getting multiplied by some matrix to get me the c coordinate vector. If I go up to what I had here, that's exactly the type of thing that I had here. I was multiplying the b coordinate vector by some matrix, and when I did that, it got me to the c coordinate vector. So what that means is this expression right here, this matrix right here, should also be a form of writing the change of coordinates matrix. Okay, and now I'm going to introduce some notation to talk about this matrix so I don't have to keep writing these words all the time. So the notation for this is we call this matrix P, and then underneath the P, we write a B here for the basis B. We put a backwards arrow pointing to C. And what that notation means is it's taking a B coordinate vector, which is written on the right in this equation, and that's outputting a C coordinate vector. So the placement of the B and the C matches the placement of the B coordinate and the C coordinate vector on the right and on the left, respectively, in this equation. Okay, so what we've just shown here is, that this equation holds, and that one of the formulas for this change of coordinates matrix is this matrix that I got here. You take all the basis vectors of B, you find their coordinate vectors in terms of the new basis C, you put those into a matrix, and that happens to be the change of coordinates matrix. So I'm going to highlight that. So, okay, so one of the things that means is this formula right here for the change of coordinates matrix is the same, it turns out, as this formula for the change of coordinates matrix. Those are equivalent. Okay, so one of the things that I'll talk more about in the next video is like, well, which one of these formulas do we use more in practice? Okay, it turns out for most of the examples that we're going to do, it's actually neither of these. It'll be the one that we will show in the next video. There's a third method for calculating this change of basis matrix that we use most often. But nonetheless, we have all of these different ways of getting to the same thing. Okay. So as a special case of using this change of coordinates matrix, what if this basis C was just the standard basis? Well, if I'm just using the standard basis, then the coordinate vector of x in terms of the standard basis, well, that's just x. That's just a normal representation of x. Okay, so if I write this equation in the special case where C is the standard basis, well, we just said the left-hand side will become x. The left-hand side will become x. On the right-hand side, we'll have this change of basis matrix. So, all these C's that I have in the subscript, those will just be the standard basis now, E. But as we just saw, when you take the coordinate vector of something in terms of the standard basis, well, that's just that vector. That's just that vector. So that means that matrix will just become, B1 ... up until Bn. All of those coordinate vectors just become the original vectors. Okay, and then this coordinate vector of x in terms of B, well, that stays there. In fact, one of the things so the big thing that we've shown here is when C is just the standard basis, this equation has just become the equation that we got back in section 4.4 when we were just going from the B coordinate vector to x. Or if I was using this equation to go in the other direction, if I had x and I was trying to solve for this B coordinate vector. So in this special case, we just get the formula that we had from section 4.4 already. Okay, so that's nice. Okay, so then this is actually generalizing our results from section 4.4. All right, so let's end this video with an example. So let's apply this change of basis matrix. All right, so I'm going to go back to that example that we started the video off with, where V is R2. I have these two bases for it, and I want to practice finding this change of coordinates matrix. So I'm going to do it using this formula that we have here. Okay, but we could do it using the first method as well. So to use this formula, I'm going to have to find the coordinate vectors of the basis vectors of B. So I'll have to find B1 in terms of C, and up until the last Bn in terms of C. Okay, so first let's find B1 in terms of C. So B1 is the vector 1, 1. What this means is express it as a linear combination of these basis vectors in C. Okay, so I'm looking for these weights. To do that, I set up an augmented matrix, and I row reduce it and I'm going to trust that we can do the row reduction. So I've gone ahead and row reduced it for us. So based on what we have here, what this means is, the entries, the weights that work are, first I have 1/4, and then I have -5/4. Okay, so that's my first coordinate vector. Okay, and if I do the same thing for B2, if I try to write B2 as a linear combination of these basis vectors in C, I would set up an augmented matrix. I've gone ahead and row reduced that one as well. And based on this, I can see that, the first entry is going to be 3/4. The second entry is going to be -11/4. Okay, so I know the columns now of this change of coordinates matrix. So I'm ready to set up that change of coordinates matrix. So its first column, let me highlight these. So the first column is this vector here. Okay, so let me go ahead and write it. That is 1/4, -5/4. And the second column is B2's coordinate vector in terms of the basis C. And I have that as well. That is 3/4 and then -11/4. Okay, and I end my matrix. And that's my change of coordinates matrix. Okay, so I'm going to box that. So now in part B, recall that when x was the vector 3, 2, I know that the B coordinate vector was 1, 1. We solved for that at the start of the video. Let's find the coordinate vector of x in terms of the basis C using this change of basis matrix. So having this change of basis matrix will make getting this coordinate vector really quick. Okay, because if I use this formula here, what it says is, well, the coordinate vector of x in terms of the basis C equals this change of basis matrix, where the columns are 1/4, -5/4, and then 3/4, -11/4. You multiply that by the B coordinate vector, which we're given is 1, 1, 1, 1. So now if I do the multiplication, multiply 1/4 times 1, add it to 3/4 times 1, that gives me 1. And then if I multiply -5/4 times 1, and then -11/4 times 1, and add those together, I'll get -16/4, which is -4. Okay, so that's my C coordinate vector. And if I scroll up to the top of the video, that is the same thing that I got when we found the C coordinate vector at the beginning, which is great. Okay, so I'm going to box this, and we have the C coordinate vector. So when we first see this, one of the questions that we might have is, this seems really long. The process for getting this change of coordinates matrix seems really long. Why bother with it when we were able to find the C coordinate vector pretty quickly by just setting up an augmented matrix like this, row reducing it, and just using our method from section 4.4? And the short answer to that is, one of the real applications of this is, what if we didn't just want to find one coordinate vector in terms of the basis C? What if we had to do 10 of these, or 20 of these, or 1,000 of these? Well, it would be very tedious to have to set up an augmented matrix for every single vector x that we could possibly put over here and row reduce all of those. But if I could find this change of coordinates matrix, although it is a little bit tedious to find it, well then to get this new coordinate vector, I don't have to do an augmented matrix anymore. I just get to do a quick multiplication. So in other words, I do the tedious part up front, but by doing that up front, now if I have to do calculations of a bunch of coordinate vectors, this makes it more efficient for me. And therein lies some of the real value of this. So in the next video, we'll talk about yet another way to find, this change of coordinates matrix. That, in our class, I think is the method that we are going to use most often. So we'll show how that works in the next video.